All right, guys. I'm going to try this again. We're doing chapter 16.5, superposition and interference. And I'm John Adams, your host. And here we go. Okay, so we've got interference and superposition. Here's the thing. There are some FETs out there. Let me see. I posted them to the website, and you'll like it. Go check out the FET website. I gave you a Fourier making waves FET website. There are other wave stuff in there. Play with all of it. There's interference. There's you name it. Just play with those things. It's really fun, and you'll learn some stuff. So that'll be even better. Because for the test, this stuff's going to factor in pretty heavily. Okay, so here's the thing. I went to one of the FETs and I took some snapshots of some of what's happening, okay? And let me just explain. We have harmonics of a standing wave situation, okay? So we have a 1 meter standing wave from the total left side to the total right side. That's in X. And we have the first harmonic, A1. We have the 9th harmonic and the 10th harmonic. Don't worry about it. We'll talk about it later. But those harmonics have different frequencies. And you can see that at 0, at X equals 0, the frequencies, the 9th and the 10th, are just about the same. They don't separate until you see maybe the first half of a wavelength. You can see they're separate. And then they gradually get more and more dispersed, out of phase with each other as they go. A1, of course, is just a really long wavelength, okay? So it's just the whole meter wavelength. All right, so what is the goal of this FET? The goal is to take these 3 harmonics and make them match to whatever this color is. I'm going to try and match the color that I see in my mind. Watch, am I close? It's this color. You're probably making fun of me, and that's okay. But at any rate, these guys right here, to me, are the same color. So that's what we're trying to match. And maybe it is, maybe it isn't. I don't know. But so our line is the black line. Okay, so I've made the A1, A9, and A10. I've made them all 0.5. Okay, and I get only a maximum of 1.5 positive and negative for any of them. So I'm going to go through and I'm going to play with these things and adjust them so that hopefully I can get them right. Okay, so let's see what the next picture holds. Okay, so this one I did fairly okay. I had to adjust A1, okay, and I adjusted A1 down to minus 0.5. And that seemed to work pretty well because I needed to have it go kind of down on the right side and up on the left side. All right, so let's try another one. I have to put it in the right position or these things won't go through. What did I do? That was number 2. This is number 3. Okay. Number 3, not too bad. I dipped down on A9. I dipped it down to 0.5, minus 0.5. And it's looking better, right? It's coming along. Our waves are kind of going in the right direction. Oh, I also moved A10 to 0.2 in the positive sense. So I'm not sure where we got to go with these to get it to work out, but we're making progress. So here's our last one. And it turns out that I had to move A1 to minus 0.4, A9 to minus 0.3, and then A10 to minus 0.9. And that gave me all three. They all add and subtract to get the right. Oh boy. They all add and subtract to get the right constructive or destructive interference. Let's look at that again. Let's go back to our original. Okay, so if you can see here, I'm going to circle a spot. Let's go black here because black, maybe green. All right, so let's circle a spot right here. Okay, all of these are going in a negative sense. Okay, all three of the harmonics are pushing in a negative sense. What does that do for us? They all add together and give us quite a negative situation. Here's another one, right? All going in a negative sense. Here we have all of them going in a positive sense. And the same goes here. And we get this. Now here, two of them are going down and one of them is going up. And so it's kind of weaker, okay? It's a weaker situation because two add together and one subtracts out. So they add and subtract in the very same space that they happen to be in. They add and subtract to each other, whether they're positive or negative. And if it's positive, then if they're two positives, then you end up with more positive. If it's two negatives, you end up with more negatives. Okay, let's get rid of all that. All right. So in the end, what did we get? We got this pretty nice wave because all of them added and subtracted the exact correct way to duplicate the wave that they gave us. Now, it's a really fun thing to do. You can go through and you can change all the amplitude controls, and you can do, I have a hard time with 5, okay? Trying to find, with 5 harmonics, solve the wave function. And you can do 10 harmonics total. You can put your amplitude controls up to 10, but they only require 5 of them. And it's really hard to do. So anyway, it's a challenge. I have yet to do the 5th. I've done the 4th and all below that, but I haven't been able to do the 5th one. That's all right. It's not a huge priority in my life. So let's see. Okay, so let's carry on here. Okay, so we've got interference and superposition. So both of those things were constructive and destructive interference. Okay, let's. I showed you constructive. Did I show you any well, yeah, I showed you some destructive. So, where do we have 2 going in one direction? Here we have 2 going in one direction and 1 going in the other. So it's not just constructive for these 2, but it's destructive for this one. It's taking away from. So it's not quite as negative at this point as it would have been because of the first harmonic is pulling us up. Okay? So that is the constructive, destructive interference that we're talking about. Get rid of those. Okay, so let's do a couple of things. Let's go to Y1. Let's make Y1 and Y2, they're essentially the same thing, okay? They're the same thing. Let's get that picture all the way out of the way. The little smiley face might be distracting. Everyone likes a smiley face. So this and this are the same wave, okay? Except for one thing, the wavelength, all right? I'm sorry. Of course, the wavelength has changed, but let's point directly at the frequency. So our frequencies are two different frequencies, means our omegas are two different angular frequencies. So what do? We want to add them together, all right? So this is our new wave. We're going to add it together. And this is what happens, all right? I'm going to take this one and I'm going to put it here. I'm going to take this one and I'm going to put it there. And then I'm going to factor out the A. And then I'm going to talk to you a little bit about the addition of cosines, okay? So when you're adding cosines, this is how it goes down. Omega 1 minus omega 2 over 2 times t. That's one cosine. Then the other one who's multiplied by it is omega 1 plus omega 2 over 2 times t. And that is what I'm going to multiply all of that stuff by this A. So I'm going to take this thing and I'm going to stick it down there. And I've got 2A times it because there's the 2, there's the A. So 2A times that thing. And now we have these. This is my overall function right here. That's my Y. That's telling me overall, this is what's going to happen in my wave. Okay. So if we're just dealing with two waves, it's very nice to deal with because we can easily see this beat frequency. Okay. And that's our angular beat frequency. And we also have an angular average, frequency average. Okay. So, and you can see it's an average because we're taking one of them, we're adding it to the other, and we're dividing by 2. So there you have it. It's an average. So our beat frequency, that's the thing that I really want to talk about. Because what is happening at the beats, well, the waves go out of phase. So here's one wave. And here's another wave. And when you combine the two, they have beats, okay? So here, they combine together. Here they combine together, but in the opposite direction. I should actually, boom, boom. Oh, I erased my one slow wave. Let's do it like that instead. Okay, adding together, so we're going to go up here, subtracting here and here, and then deconstruction here. But how do I want to do deconstruction? Well, I'm going to leave it. And then we're adding in this direction together. So you can do something like this overall. You can see where the beats are happening, where they're adding constructively together in places. And that's going to give you a good beat frequency, or the overall large amplitudes are the beats, okay? And you sometimes, I don't know, maybe you guys don't feel this kind of stuff, but your heart will do some weird things, and you'll actually feel it. It'll be pounding. Well, it's a combination of different cycles in your chest that are coming together for that beat, okay? And it gives you a really strong beat, and then it goes back. In fact, your heart, it kind of wants to go like this. All the frequency stuff is nullified in this area and this area, and then it allows the beat frequency to come through and give you this and then all the rest of them add up to nothing. So every once in a while you get this really, really strong beat. Well, that's your heartbeat, okay? That's your beat frequency. Okay, so fine. Let's move on. Let's go to the next one. The next one is, oh, I didn't set my timer. Set timer for 30 minutes. The next one, we have a sine of kx minus omega t plus phi, okay, because I want to introduce a phase angle, all right? We have y2 is sine of kx minus omega t, no phi, all right? So here's what we do. We add them together. We want to get y equals y1 plus y2. Where can I put that? I'm going to put y equals y1 plus y2. All right, that's what we're doing here. Now, we are adding sine of all that jazz and cosine of all that, or not cosine, sine of all that stuff. And here's a nice way to do it. We're going to make this A, or alpha, and this one beta, and then we can do the sine, 2 times the sine of alpha plus beta over 2 times the cosine of alpha minus beta over 2 is equivalent, okay? So let's just see where that takes us. All right, well, first of all, alpha plus beta is going to be kx minus omega t plus phi plus kx minus omega t. So we'll have 2 of those things. And the only thing that keeps the 2 in the bottom would be the phi over 2. Okay, so that gives us, that first sign gives us this. But when we do alpha minus beta, we're going to be left with nothing but the phase angle. So that leaves us with the phase angle over 2, the cosine of the phase angle over 2. But that's a constant, okay? Phase angle over 2, that's just a constant. So we're going to say, all right, great. I can slap that out front and make all of this part of my new amplitude. We could call it A prime if we want. And we have some new amplitude. And then we've got the sine of kx minus omega t plus phi over 2. Now phi over 2 is my new phase angle. So phi prime is the new phase angle, which is originally phi, but we are dividing it by 2. We're still going to the right, okay? We still have this kx minus omega t, so that leads us to going to the right. And everything seems great. And if you look at our phase angle difference, we have just changed a little bit. Instead of going, let's go green here. Instead of starting out here and going like this, we've started at a little bit off of that and are going north of that, up from there. All right, on the black line. Okay, let's talk about standing waves. So standing waves. This, my friends, is a really, really fun one, okay? So we have some distance. Let's do this distance that we're going to keep a constant. It doesn't matter what it is. We can just call it L. And at some point, x along that, we could say x equals 0 here, and go all the way from x equals 0 to x equals L. And we're going to have waves that we initiate and send into this situation. And of course, the waves, there's no friction, so we can start a wave just like at Bronco Stadium. We start the wave, and then it keeps on going and going and going and never stops. You know, you've all been there. You've seen that. All right. A sine kx minus omega t, we're going to turn into alpha. All right, so that's our alpha. And then we've got kx plus omega t, that's our beta. So believe it or not, I look into alpha plus beta, alpha minus beta. I do this. I have to go look up the trigonometric functions every time. Nobody memorizes these things. So if you need a trigonometric equation on your test, I'm going to be there for you. I'm there for you. I am not going to murder you on that. I'll provide. Okay, so you'll have it. You don't even need to write down a whole trigonometric book of identities because you're not sure which one you're going to need. So I'm going to have them. If you need it, it'll be there. So, okay, alpha plus beta over 2, that's our first sign, alpha plus beta over 2. Well, we're going to take alpha plus beta. That's going to get rid of our omega t's. And we're going to be left with kx over 2. 2kx over 2. Which, of course, is just kx. All right? So that's our sign of kx. And I called it a constant. And I don't want to refer to it really as a constant. I'm going to tell you why in a second. Let's just keep it like this. I recorded this already once and I didn't like it, so I'm coming back and we're doing it again. Okay, so we've done alpha plus beta over 2. Now we have to do alpha minus beta over 2. Well, that's going to give us minus 2 omega t's over 2. So the 2 goes away, we're left with minus omega t. Now, you guys may or may not remember this, but if you have the cosine of a negative angle, it's equal to the cosine of the positive angle. So why deal with a negative if you don't have to? I don't like it. So I'm going to get rid of my negative and just take that out. Okay? Just like that. It's just that easy. Y as a function of x and t now becomes our new a prime. All right. Now I haven't really talked about why we're considering this not part of the situation. And the reason is because for every x, it's going to have this mishmash of things happening. Okay, so it just happens that I went through the node at that one point. But this x, no matter what happens, is going to have this amplitude. Okay, and it doesn't matter. So whatever that x prime is, it's going to have that amplitude. That's it. That's all we get. All right, this will have the max amplitude here. And it's all because of this sign of kx not moving, okay? The x doesn't change. The k doesn't change. Everything's going to stay the same. I shouldn't say the k doesn't change, but the k doesn't change. Okay, for our situation. But what could change is our omega. Okay, our frequencies. We could send in different frequencies up and down. We could make it be fast, slow, all kinds of stuff. So our frequencies are variable. Fine. So now we have y of x of t is equal to a prime cosine of omega t. And that's it. We're back to kind of almost like square one. And then all of our equations go in to fit this omega 2 pi f. We can get our period. We can do t over 2 is, why is t over 2 our time that we want to deal with? Okay, now we're talking about actually doing a little bit of interesting stuff here. So, since we're only looking at cosine omega t, and we want to choose the waves that are in phase, and things that are in phase, let's see, t over 2. So if we start here and we go down, we go up, this is 1 period. And we want t over 2, we want the node. So what is happening at the node? How do we find these nodes? Well, it's every time we're at t over 2. Well, that's equal to, we're going to put in our period divided by 2. That's just this, okay? That equals t over 2. So we've got pi over omega, all right? So pi over our angular frequency. But how many times is that going to happen? That's going to happen here. That's going to happen here. It's going to happen all over the place. So every single time that we have t over 2, so essentially what I'm doing is I'm going to this equation right here. Our time is equal to n times t over 2, and this is for all n, all integer n's from 0 to 100. Now this is where the wave number thing comes in, okay? And I know I threw it behind quantum mechanics when I was talking about it in class, but it really isn't. But here's the real thing. They knew about this in the 1800s, and they didn't say, "Oh, wow, this is why quantum mechanics has integer stuff," because they didn't know about quantum mechanics. And this is exactly why quantum mechanics does integer things, okay? And there are integer steps because particles live in small places, small confined places, and they have to have the same boundary conditions that anything else has, right? So they're in a confined space. It's just like a string on a wave, and they can only have so many types of frequencies that happen, okay? And that's what we're talking about. So to get the nodes where we want them, we have to have n equals 0, 1, 2, and we plug those into this n right here, and then that way we can have, we'll know exactly where the nodes are for our situation. Y1 and Y2 are in phase at these points, okay? They're in phase. Now, if we want to look where they're out of phase, let's go back to our picture. Well, we're certainly out of phase here, all right? So that's t over 4. This one, we're super out of phase. That is 3t over 4. Here, we're at 5t over 4, and here we're at 7t over 4. So, out of phase, all right? So, out of phase is this, n t over 4. But n can't be even at all, ever. If it's even, then it cancels out and we're back to in phase. So odd, n is 1, 3, 5, blah, 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 into infinity of odd n's, okay? And I drew a better picture here. This is a much better picture showing you these points. Much better picture of showing these. Now these are called, well, that's a node. Well, no, I guess that's corresponding to this. These are antinodes, okay? So we've got nodes and antinodes. So forget about this picture. That's no good. Nobody likes that picture. Antinode and node. All right, so here are our nodes. And we can call this a node, but it's really a boundary because it's forced to be there. But for sure, the ones in the middle are nodes. And then these guys are antinodes. All right, so antinode here and node here. Now, if we're dealing with the sign of kx instead, so what have I done? I have moved everything, instead of on the t-axis, I've put it on the x-axis. So now our x can change, but our t is essentially staying still. I don't know. You're like, how does time stay still? Okay, time's not staying still. Everything's moving, but we're gonna deal with kx instead. We wanna deal with the wave number, okay? And I talked about the wave number today in class. So the wave number, what is that? That in units, that's radians per meter, because lambda. What is lambda? You have to ask yourself. I asked the class this the other day, and everybody's like, oh, I don't know what lambda is. Lambda is equal to your wavelength. So lambda is the wavelength. It's in meters, SI. You want to do the SI unit. And then if you've got 2 pi over your wavelength, you've got your wave number. Again, this comes back to, in a way, quantum mechanics, but you don't have to think about it in terms of quantum mechanics, because this is a real life thing. We see it every day. And we see quantum mechanics all the time. People just don't single it out as that. Okay, so where do we get nodes? So if we're looking in the x-axis, we get nodes when kx is equal to plus or minus pi. All right? So when does that happen? Well, x equals 0, x equals pi over k, 2 pi over k, and so forth and so on, which leads us to n pi over k, and that means n lambda over 2. Okay, so x equals these things, and we can sum that whole thing up like this. X equals n lambda over 2 for all n, okay? All n. And that is telling us where our nodes are. Antinodes. Well, it's a very similar thing. We have kx equals pi over 2, right? Because we're not going all the way to pi. We're going halfway. That's pi over 2. And then 3 pi over 2, 5 pi over 2, so and so and so and so. And that gives us x equals lambda over 4, 3 lambda over 4, 5 lambda over 4. You get the picture. It's all about lambda over 4. How many times? We're going to do n equals 1. We can go to the next one, n equals 3, 5, and so on, but they all have to be odd. So that gives us our antinodes. Okay, very similar situation. Well, this is turning out a heck of a lot better than last time, and I'm glad I'm redoing this. I don't know if I like this picture a whole bunch, but okay, here you go. For all the music lovers out there, I've got a stand. Okay, here's a stand. It's got a string attached to it right here. And then over here, I've got a speaker. And you guys have seen speakers. They vibrate. They go in and out with certain input frequencies. We're calling it an input frequency, but the speaker has its its frequency, whatever it is. We're driving it with some sinusoidal wave. So it's doing this. We're driving it with that. And hopefully we're doing it with a certain resonance to this situation. I'm going to just say that our length is from here to there. So I'm going to do this real quick. And we've got an input frequency. Our input frequency is driving the speaker, okay? And we can change this input frequency. We can make it whatever we want, okay? We've got control. So this thing's going up and down. Our little post on the speaker is going up and down. What does that do? That shakes our, at a certain frequency, it lifts and pulls back down our wire, our line, our string, whatever you want to call it. All right. So I've got a really cool drawing that I'm looking at, and I did. Oh, it's so good. If only you guys could see it. Okay, let me see if I can recreate this thing. Oh, let's go back to black here. Okay, there's one. Okay. Let's do green. What do I have? Oh, my brain is... I've got reds and greens, all these things happening. Okay, I've got a green going like this. So this comes back to our, did I pick yellow yet? Boom, boom, boom. Let's do this one. But this time we're going to go all the way across. And let's do this one. No, I don't want that. I want blue. I say blue, but it could be anything. Who knows? All right, let's do a black one. Okay, well, no, green. Because green's got to go back like that. They all have to reproduce on the other side as well, right? So yellow. Something like this. And where does that leave me with this blue thing? Okay. I think you guys can see what I'm talking about. When we have the right frequency, we're going to get different nodes. So if we want blue, we have to make our speaker give us the right frequency. Keep in mind, of course, this thing has to be under the correct tension, okay? So there has to be some tension between one side and the other on the string. Otherwise, there won't be any restoring force, and then nothing happens, and you're shaking a wet noodle at somebody. So the frequencies are, blue is the highest frequency. Okay. Blue. I shouldn't even call it a color. It could be I don't know what color it is. I don't know why I'm saying blue or anything. Whatever color this is the highest frequency. HIGHEST, highest frequency. Okay, then we have red is the lowest. Next step down would be what? Yellow? Do I have yellow and green in there? Oh god, I'm dying. Colors are bad, hard for me. Okay, I think this is the next step down. Then I think this one is the next step down. You guys have to forgive me if I don't have this correct. Like this thing could be brown. I keep calling it red. I don't know. Who knows? Okay, so that's my lowest. All right. So those are our frequencies going from our speaker. And when we are hitting those harmonics hardest, we're going to get nodes and antinodes at those places. In between, okay, in between is no man's land. You get nothing. You get gibberish, static, blah. So everything in between here and here is static. It's nothing. It gives you just chaos, okay? So there's one frequency that works, and everything in between is junk. One frequency that works, junk. So these frequencies are what we call harmonics. All right, these are the harmonics. And these are the things that I was dealing with. Harmonics. These are the things I was showing you at the very beginning. I had the lowest harmonic, and then we worked up from there, okay? And we had, what, 10? So yeah, there are 10 if you want. In that situation, we could have used all 10. I was only working with 3. So let's talk about this for a second. If we say, we were talking about the n's up here, right? We've got n is this and n is that and all those other things. Well, we can say n equals 1, okay? So, did I say 0? You can't have 0. So hold on a second, everyone. Hang on. You gotta go away. Okay, that's better. I feel better now. I'm doing this other thing. I didn't get rid of all the zeros. This has to go away too. You gotta go away. All right. Sorry. Sorry, everyone. I'm doing this thing and I'm dealing with zeros, and zeros aren't supposed to be a part of this. Okay. All right. So let's get back to it. Let's talk about n equals 1. I set my hand down and this thing goes nuts. N equals 1. What's going to happen here? So I have 1/2 lambda 1 equals my length. Okay? That takes us to lambda 1 is equal to 2 times L. And if you notice, that's exactly what was happening here. Okay? If I were to draw the entire length of this wavelength, I'd have to go all the way out 2 times L to get my total wavelength for n equals 1. So I'm not doing that, but that's what I could be doing. I'm going to get rid of all these little guys down here. Okay, I could be doing that, but we're only dealing with the n equals 1, all right? So just, if you have n equals 1, all you're going to see is one antinode and the 2 end boundaries, okay? That's it. Well, here's the solution to that. Here's what this means. Before I do, let's go back here. So tau, our period is n equals 1. So our period is for the antinode n times t over 2. Okay, and in phase and out of phase, n times t over 2. So we want in phase. There's a 0 again. Oh, God. N times t over 2. Die. So our frequency is F1. How did I get that color? You guys probably remember. F1 equals 1 times VW over 2L. Just forgive me for a second. I'm going to show you where this comes from in a second. Okay? Over 2L. So that's my n equals 1. And this happens to be our natural frequency for the situation. Okay? So when you only have the one node, no nodes, but one antinode, you're dealing with the fundamental frequency. Okay, so fundamental. Now, okay, why do we have F the way we do? Okay, so here, let's do it. So lambda, let's say lambda n times Fn is equal to our velocity of the wave. But we've already said that lambda, let's say lambda, well, okay, let's solve for Vn. Then that means over lambda n. But let's just do lambda at 1. Okay, so we've got 1/2 lambda 1 equals L. That takes us to, oh, I already have it written down here. Lambda 1 equals 2L. So for F1, I'm going to take VW and divide by 2L. And there you have it. Okay? That's it right there. Awesome. So we have our fundamental frequency and what that fundamental frequency is doing. Set timer for 10 minutes. N equals 2. That's going to give us lambda 2. And that equals L. So our F2 is 2 over 2 times VW over L. And there are a lot of ways you can write that because you want to kind of keep your 2 in there, right? You want to keep the 2 available. But this is that's what you're left with, okay? So that equals your second frequency, okay? So you know the length, and you know your speed through the medium, maybe. So you can take those two things and figure out what your frequency input should be to get two antinodes. All right, this gives you 2 antinodes. This is what we call the first overtone. All right, this is our first overtone. N equals 3. Obviously, our second overtone. And let me write, it's 3/2 lambda L. So that gives us lambda 3 is equal to 2/3 L. And our F3 then is 3/2 VW over L. Okay, that's our second overtone. And that would actually give us the 3 antinodes. Fourth overtone. I'm not gonna write it all out this time. I'm just gonna say lambda 4 is equal to L over 2, and our fourth frequency, so this is third overtone. F4 is 4/2. I'm going to write it as 4/2, okay, because I want you guys to see the half thing, okay? So I want you to work with this. All right. What can we say about this? We're gonna figure out how we can nail this down mathematically. We've got 2n over L for our lambdas, and our frequencies are Fn is equal to n times our VW over 2L. If you notice, we've got a 2L in the bottom of each of these, and we're only adding, we go with 2 here, 3 here, 4 there, so that's our n, okay? And we're going to do it for all. This is the for all symbol. If you ever see that, that just means they're doing it for all. But I'm not going to use that symbol at the moment. So we're doing it for all n equal to 1, 2, and 3. What do we get out of this? We get that F1 is our natural frequency, also known as resonant frequency. All right, the fundamental frequency. Man, how many words? Fundamental. That's another one. Okay, anytime somebody says natural, resonant, fundamental frequency, in fact, resonant, they're all resonant. It's the most resonant. So let's stick with these two, fundamental and natural. They all resonate with this thing, but this one resonates hardest. The F1 is the most resonant. Okay, the other ones also resonate, so I don't know if calling it a resonant frequency is the proper thing, but it's certainly the most fundamental or natural frequency, okay, for this item. So let's do an example. If we do an example real quick, we'll have this whole thing licked and we'll be done. Okay. So here's our situation. We've got our ability to send in frequencies to this wire, or it could be a wire like in a piano, it could be whatever. We don't know. Something firm on this end, and then something that allows us to put a frequency generation in on this side. And we're going to start doing frequencies. Okay, I'm going to give you some information. So here's what we're going to do. I'm going to say our velocity is 52 meters per second, and our length is equal to 2.0 meters. And what I want you to do is do 3 things, and you can pause the video and then come back. And if you didn't do it right, that's fine. We can go through and you can... So what is the fundamental frequency? First, that's A. B, what is the first mode? What is the first lambda? Okay, so we get the frequency, and then we're going to want to get the lambda 1. Okay, good. And then what is the frequency for the fourth overtone frequency? What is the fourth overtone frequency? Okay. So pause the video, go through, do those things, and then come back, and we will talk about the answer. Okay, get ready, set, pause. Okay, so we're back. And I love it's so good, this magic of video. It's exciting. Okay, so what is the fundamental frequency? Well, F1, so we're just doing A here. F1 is equal to our velocity of the wave divided by 2L, okay? Because we're multiplying by n equals 1. So that's what we're dealing with, so we can put those numbers in. We've got 52, and we're going to divide by 4. That happens to be 13 because I've played with a deck of cards, and anybody who has knows that there are 13 cards per suit. So we're dealing with F1 equals 13 hertz. I didn't put any units in, but if you want, you've got meters per second, and we're dividing by meters. That leaves us with 1 over a second, which is equal to a hertz. So that's if you want to look at the units of the situation, there you go. Now, B, what is the first lambda 1? Okay, so lambda 1. How do we want to do this? Well, there's a couple of ways, right? There's a couple of ways to do this. We could say lambda 1 is equal to 2L over n. And of course, n equals 1. So we're left with 2L. 2L, well, we already know that we were dealing with 2L anyway. But that ends up being our 4.0 meters. Another way to do this is our velocity of the wave is equal to our frequency times our lambda. And we could solve that if we insert 1s on both of these things. Then we can say VW divided by F1 is going to give us our lambda. And of course, we're dealing with 52 divided by 13. And that's going to give us our 4.0 meters. Okay, C. Come on, baby. There we go. What is the frequency for the fourth overtone? Oh boy. So we're dealing with N1. N equals 1 is fundamental. All right. N equals 2, first overtone. N equals 3, second overtone. N equals 4, third overtone. N equals 5, fourth overtone. So we need N equals 5. Okay, fine. Now what? What is our question? The frequency. We want the frequency. So we go to our equation and we say f of n equals n times VW over 2L. Great. We're going to put in fives for all this. So F5 is equal to 5 halves VW over L. Our length is 2, so VW over 2 is 26. We could divide again by 2 and get 13. So then we're left with 5 times 13. That works. And we'll see that, what do we get? 5 times 13, carry the 1, 65 hertz. I laugh about carry the 1. Okay, so that's it. So great. I'm glad. Thanks for paying attention. And we're all set here. Oh, here we go. Let's kill this thing.